The James Webb Space Telescope is living up to its promise as a wayback machine. Impossible ancient galaxies, massive cosmic structures, and the possibility of alternate universes all are discovered by James Webb. This telescope is just reshaping our cosmic perceptions. But with these groundbreaking discoveries made by James Webb, are we on the brink of unraveling the greatest cosmic mystery? Is this just the beginning of a whole new chapter in our cosmic adventure? Join us as we dig deep into how James Webb could take us to the end of space. The James Webb Space Telescope was humanity's first pioneering attempt in capturing the first lights in the universe. This marvelous structure, half as big as a 737 aircraft, with a sun shield the size of a tennis court, was made at a budget of around $10 billion, with the relentless effort of scientists from the NASA, ESA, and the CSA for over 3 decades. Despite its groundbreaking potential, James Webb faced a journey filled with hurdles since 1996. Finally, the telescope's construction was completed in 2016, and after a set of tests, James Webb was all set to launch in March 2021. Just when everyone thought that the telescope was all set to seek the final frontiers, they were reminded that it is not over until it is over. Following a series of postponements and rehearsals, it was ultimately launched on December 25, 2021, atop an Ariane 5 rocket from Kourou, French Guiana. This marked the commencement of a journey to seek the answers to the biggest questions of humanity. Renowned as the successor of Hubble, James Webb boasts a significant advancement over its predecessor with a 6.5-meter diameter gold-coated beryllium primary mirror, comprised of 18 hexagonal segments. This mirror, 6 times larger than that of Hubble's, provides a light-collecting area of 25 square meters, enabling the observation of objects too faint or distant for Hubble. Operating primarily in the near-to-mid-infrared spectrum, James Webb can delve into the mysteries of the early universe, studying the first stars, galaxies, and potentially habitable exoplanets. The telescope's design also addresses the challenges of infrared observations, necessitating extremely cold temperatures below 50 Kelvin to prevent interference from its own infrared emissions. The 5-layer sun shield shields it from the sun, earth, and moon's warmth. This focus on the infrared spectrum is crucial, as high redshift objects emit visible light shifted into the infrared, and infrared light penetrates dust clouds more effectively than visible light. It was equipped with a sophisticated array of instruments housed in the Integrated Science Instrument Module, a structural framework that provides essential functions to the telescope. The Integrated Science Instrument Module, made with bonded graphite epoxy composite, had to support the 4 primary science instruments and a guide camera. The intricacies of these instruments highlight the collaborative efforts of international teams in advancing our understanding of the universe through the groundbreaking James Webb Space Telescope. Our naked eye would never be able to see what the telescope sees. Traveling through light and space, NASA's James Webb can see the origins of the universe, something our minds can hardly begin to grasp. Working like a time machine, the telescope promises to take us far enough to put together the broad strokes of how our universe grew up, and it's looking like a story that will lead to decades of additional research to robustly put all of the pieces together. And right from its very first deep field image, unveiled by President Joe Biden, Vice President Kamala Harris, and Nelson Live at the White House, Webb has delivered on its promise to show us more of the universe than ever before. However, Webb revealed much more than distant galaxies in the early universe. According to Eric Smith, Associate Director for Research in the Astrophysics Division at NASA headquarters and Webb program scientist, the breadth of science Webb is capable of exploring really becomes clear now, when we have a full year's worth of data from targets across the sky. Webb's first year of science has not only taught us new things about our universe, but it has revealed the capabilities of the telescope to be greater than our expectations. meaning future discoveries will be even more amazing. The global astronomy community has spent the past year excitedly poring over Webb's initial public data and getting a feel for how to work with it. Beyond the stunning infrared images, what really has scientists excited are Webb's crisp spectra, the detailed information that can be gleaned from light by the telescope's spectroscopic instruments. Webb's spectra have confirmed the distances of some of the farthest galaxies ever observed and have discovered the earliest, most distant supermassive black holes. They have identified the compositions of planet atmospheres, or lack thereof, with more detail than ever before, and have narrowed down what kinds of atmospheres may exist on rocky exoplanets for the first time. They also have revealed the chemical makeup of stellar nurseries and protoplanetary disks, detecting water, organic carbon-containing molecules, and more. Already, Webb observations have resulted in hundreds of scientific papers answering long-standing questions and raising new ones to address with Webb. The breadth of Webb science is also apparent in its observations of the region of space we are most familiar with, our own solar system. Faint rings of gas giants appear out of the darkness, dotted by moons, while in the background, Webb shows distant galaxies. By comparing detections of water and other molecules in our solar system with those found in the disks of other, much younger planetary systems, Webb is helping to build up clues about our own origins, how Earth became the ideal place for life as we know it. As Webb senior project scientist Jane Rigby of NASA's Goddard Space Flight Center said, "With a year of science under our belts, we know exactly how powerful this telescope is and have delivered a year of spectacular data and discoveries. We've selected an ambitious set of observations for year 2 that builds on everything we've learned so far. Webb's science mission is just getting started. There's so much more to come." Indeed, in a stunning discovery, James Webb has just captured a glimpse of the earliest strands of the cosmic web. Galaxies are not scattered randomly across the universe. They gather together not only into clusters, but into vast, interconnected filamentary structures, with gigantic barren voids in between. Cosmologists call this structure the cosmic web. The cosmic web holds the vast majority of the contents of the cosmos, roughly 5% matter such as gases and solids, 27% dark matter and 68% dark energy, and it spans the entire universe, traversing otherwise relatively empty cosmic voids. It serves as the scaffold responsible for carrying the plasma lifeblood of our universe. It is the reason we exist at all. However, it is devilishly hard to get a handle on. For one, it's invisible. We can only begin to discern its filaments' contours by spotting galaxies, as those that emerged in the Stickman. Also, it's just really big. The cosmic web fills up the volume of the universe and contains up to 2 trillion galaxies, of which we've mapped far less than 1%. But mapping the web wouldn't just provide us with a better picture of our universe, it also promises to reveal tantalizing information about some of the biggest questions in cosmology, about what dark matter and dark energy are, how they behave, and whether they change over time. And answering those mysteries might reveal the ultimate fate of our universe. Efforts using tried-and-true astronomical models to develop a cartography of the cosmic web have continually come up flat. So astronomers are taking up some unconventional approaches, applying principles of origami, spiders' webs, and even slime molds to try to understand the structure of this life-giving network. And now, like a giant leap, astronomers using NASA's James Webb Space Telescope have discovered a thread-like arrangement of 10 galaxies that existed just 830 million years after the Big Bang. The 3 million light-year-long structure is anchored by a luminous quasar, a galaxy with an active, supermassive black hole at its core. The team believes the filament will eventually evolve into a massive cluster of galaxies, much like the well-known Coma cluster in the nearby universe. And it's, put simply, far exceeding expectations. Scientists expected to find something, but they didn't expect such a long, distinctly thin structure. And according to Feige Wang of the University of Arizona in Tucson, the principal investigator of this program, this is one of the earliest filamentary structures that people have ever found associated with a distant quasar. These Webb observations are part of an observation program called ASPIRE, a spectroscopic survey of biased halos in the reionization era. It uses both images and spectra of 25 quasars that existed back when the universe was starting to light up after the Dark Ages. The idea is to study the formation of the very earliest galaxies possible, as well as the births of the first black holes. In addition, the team hopes to understand how the early universe was enriched with heavier elements and how it all played out during the epoch of reionization. The ASPIRE goals are an important part of understanding the origin and evolution of the universe. It aims to understand how to incorporate the emergence of the earliest massive black holes into our current story of the formation of cosmic structure. Quasars beckon across time and space. They're powered by supermassive black holes which produce incredible amounts of light and other emissions, along with powerful jets. Astronomers use them as standard candles for distance measurements, as well as a way to study the vast regions of space their light passes through. At least 8 of the quasars in the ASPIRE study have black holes that formed less than 1 billion years after the Big Bang. These black holes have masses of between 600 million to 2 billion times the mass of the Sun. That's really quite massive and raises a lot of questions about their rapid growth. Indeed, to form these supermassive black holes in such a short time, 2 criteria must be satisfied. First, you need to start growing from a massive seed black hole. Second, even if this seed starts with a mass equivalent to 1,000 suns, it still needs to accrete 1 million times more matter at the maximum possible rate for its entire lifetime. What's more, for these black holes to grow as they did, they needed a lot of fuel. Their galaxies were also quite massive, which could explain the monster black holes in their hearts. Not only did those black holes suck in a lot of material, but their outflows also affect star formation. Scientists point out that strong winds from black holes can suppress the formation of stars in the host galaxy. Such winds have been observed in the nearby universe, but have never been directly observed in the epoch of reionization. The scale of the wind is related to the structure of the quasar. In the Webb observations, we are seeing that such winds existed in the early universe. It's interesting that those early galaxies James Webb found, along with their quasars, were already fully in place, with supermassive black holes at their cores. That key question remains: how did they get so big so fast? Their existence may tell astronomers something about the overdensities in the infant cosmos. First, the black hole seed needs an overdense region filled with galaxies in order to form. However, so far, observations before the James Webb discovery found only a few galaxy overdensities around the earliest supermassive black holes. Astronomers need to do more observations at this epoch to explain why that might be. The ASPIRE program should help resolve questions about the feedback between galaxy formation and black hole creation in this very early epoch of the universe. So, along the way, we should also see more fragments of the large-scale structure of the universe's cosmic web as they form. A remarkable finding for the first time, astronomers have detected dark matter hanging from massive filaments that stretch across the universe and form a cosmic web that trap galaxies like morning dew on a spider web. Researchers from Yonsei University in Seoul, South Korea, used the Subaru telescope, an 8.2-meter optical infrared telescope near the summit of Mauna Kea in Hawaii, and an effect that gravity has on light to indirectly observe dark matter sitting on cosmic web filaments in the Coma cluster. This marks the first ever detection of dark matter on the cosmic web, and could help confirm how this structure, with strands that run for tens of millions of light years, has influenced the evolution of the universe. Also known as Abell 1656, the Coma cluster is a collection of over 1,000 galaxies and is located some 321 million light-years away from us in the direction of the constellation Coma Berenices. Because of this tremendous size and relative proximity, the Coma cluster is an ideal place for scientists to hunt dark matter on cosmic web strands. The cosmic web is a network of filaments made up of matter that feed gas into galaxies, helping them grow. This web also helps channel galaxies together, leading them to cluster. The main filaments of the cosmic web are themselves the walls of galaxy superclusters, with the wall corresponding with the Coma cluster. Great Wall. The Great Wall was actually the first super-large structure in the universe to be discovered. Clusters of galaxies are believed to gather at points where filaments intersect. But these filaments are believed to terminate between galaxies and form what are called intra-cluster filaments. Dark matter is expected to run along these cosmic web filaments, dangling from those intra-cluster filaments. Though the cosmic web, the largest structure in the universe, has been known about for decades, astronomers have only seen the faint glow of its gas filaments when they have been illuminated by bright regions at the hearts of galaxies powered by feeding supermassive black holes. Those active black holes are called quasars. Last year, the Keck Cosmic Web Imager, also atop Mauna Kea, caught the first direct light emanating from wispy web filaments that cross one another and stretch across the darkest corners of space. These are filaments that sit isolated between galaxies in the largest and most hidden portions of the cosmic web. Seeing the location of dark matter around these cosmic web strands is a completely different story, however. That's because despite making up an estimated 85% of all the matter in the universe, dark matter is invisible because it doesn't interact with light like everyday matter that comprises stars and dust does. Dark matter's dominance over everyday matter also means it dominates the filaments of the cosmic web, forming an invisible scaffold along which the universe's structure takes shape. However, even though dark matter doesn't interact with light, it does interact with gravity, and this interaction impacts the movement of everyday matter and light that we can see. The team behind this research took advantage of this concept, using it to detect dark matter on cosmic web filaments threaded throughout the Coma cluster. Albert Einstein's 1915 theory of gravity, called general relativity, suggests that objects with mass cause the fabric of space-time to curve. In turn, the theory explains what we perceive as gravity arises from this curvature. Furthermore, when light from a background source passes through this curvature, its path gets diverted. This can lead to background sources appearing to shift in the sky, to be amplified, or in some extreme cases, even to appear at multiple points in the same image. This is called gravitational lensing. So, using light from galaxies and stars behind the Coma cluster, and assisted by the high sensitivity, high resolution, and wide field of view of the Subaru telescope's hyper-suprime cam, the team detected a weak lensing effect of the dark matter component of intra-cluster filaments for the first time. This first-ever detection of dark matter on terminal segments of the cosmic web helps to further confirm the existence of the large-scale structure spreading across the universe. Meanwhile, in vast space, it would appear that Sagittarius A star got into the spirit of the Super Bowl. The supermassive black hole at the center of our Milky Way galaxy is spinning so fast that it is warping space-time into an oval shape reminiscent of an American football. The finding comes from a careful study of radio and X-ray observations. According to Albert Einstein's theory of general relativity, when a massive object is spinning, it can drag space-time around with it. This phenomenon is called frame dragging, and even our spinning Earth has been observed to warp space-time in its vicinity. However, the effect is far more pronounced for extremely massive objects, aka supermassive black holes that are many millions or even billions of times more massive than our Sun. And the more quickly such a massive object spins, the more space-time flattens around it, thereby adopting that oval shape. However, the spin rate of our galaxy's 4.1 million solar mass black hole which is called Sagittarius A star, has been difficult to pin down. Most estimates have varied widely. A group of astronomers, led by Ruth Daly of Penn State University, has now applied a procedure called the outflow method to get a measure of Sagittarius A star's angular velocity, that is, how many times it spins per second. The outflow method is quite literally named. It measures how material is flowing away from a black hole, which might at first seem counterintuitive, as black holes are more well known for pulling material in. Yet, an outflow from a black hole can come in the form of a magnetically collimated jet of matter that emits copious radio waves. Meanwhile, hot clumps of plasma produced in the disk of matter around a black hole, and which can then drift away, are hot enough to radiate in X-rays. These clumps, called plasmoids, form more efficiently when a black hole is spinning rapidly because the resulting frame dragging amplifies the black hole's magnetic field and tightens it like a belt closer to the black hole's periphery. In turn, this creates magnetically intense conditions more conducive to plasmoid formation. So, by going back to archival observations of the black hole made with the Carl G. Jansky Very Large Array of Radio Telescopes and NASA's Chandra X-ray Observatory, Daly's team measured the angular velocity of Sagittarius, a star, to be 60% of the maximum possible value, which is defined by the speed of light. In other words, this black hole is spinning very fast, quick enough to warp space-time into a flattened oval shape. And it's really interesting and has far-reaching implications. These implications relate to the past and possible future activity of Sagittarius A star. The faster a black hole spins, the more powerful the collimated jets of radiation it emits as particles in the hot disk of matter swirling around the black hole are swept up and spat out. Currently, Sagittarius A star is barely active, but the infall of an unfortunate gas cloud or star could refuel its jets. Evidence that this has happened in the past comes from what are called the Fermi bubbles, which are two humongous structures of gamma-ray emitting matter stretching above and below the plane of our galaxy, spanning 50,000 light-years in total and centered on Sagittarius A star. The belief is that the Fermi bubbles are remnants of powerful jets that once blasted out from the black hole, but such powerful jets could only arise if Sagittarius A star is spinning rapidly. Structures such as the Fermi bubbles are able to excavate gas from a galaxy, careening through star-forming material like a snowplow. As Megan Donahue of Michigan State University in the same press statement, jets powered and collimated by a galaxy's spinning central black hole can profoundly affect the gas supply for an entire galaxy, which affects how quickly and even whether stars can form. The Fermi bubbles seen in X-rays and gamma rays around our Milky Way's black hole show the black hole was probably active in the past. Measuring the spin of our black hole is an important test of this scenario. In addition, a newly discovered asteroid snuck safely between the Earth and Moon during a very close encounter this week. On February 12th, an asteroid named 2024 CY1 traveled within 121,148 kilometers of Earth, which is about 31% of the average distance between the Moon and Earth, 384,400 kilometers, also known as lunar distance. And according to the Virtual Telescope project, the asteroid's close approach occurred at 2:24 a.m. Eastern Time. The asteroid 2024 CY1 was just recently discovered on February 9th, only 3 days before its close approach. Astronomers spotted the asteroid using the Pan-STARRS 2 telescope located near the summit of Haleakala on the island of Maui, Hawaii. It is the 10th known asteroid to fly past Earth within one lunar distance in 2024 so far, and the third this month. Pan-STARRS 2, which stands for Panoramic Survey Telescope and Rapid Response System, is designed to hunt for near-Earth objects, such as asteroids and comets, that may pose a risk for potential Earth impact. Most near-Earth objects are asteroids that range in size from about 3 meters to nearly 40 kilometers across. Measuring between 3.8 and 8.4 meters in diameter, 2024 CY1 is a relatively small asteroid, posing no risk to Earth. Near-Earth objects have orbits that bring them to within 195 million kilometers of the Sun, meaning they can pass through Earth's orbital neighborhood. The distance between the Earth and the Sun is measured in astronomical units, where 1 astronomical unit is equal to about 150 million kilometers. During its recent flyby, 2024 CY1 traveled at a distance of 0.0081 astronomical units. The asteroid, 2024 CY1, belongs to the Apollo group of near-Earth asteroids, which includes asteroids that cross Earth's orbit. Using instruments like Pan-STARRS 2, astronomers are able to calculate an object's orbit and determine if and when it could come close to Earth. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.